see how this works. I'm really here representing our climate research team, and we call ourselves the Right Climate Stuff, named after guys like Walt Cunningham, who first coined that phrase, the right stuff. So what I'm presenting today is kind of a collective work of our team. I've done some of the original modeling, but they have been very critical and helped me refine this over the last couple of years. We're just finishing up our third year of study at ICCC10, I think it was, in Chicago. We had just started. We didn't know anything about climate, and we were just beginning. I forgot who it was. Joe Bass probably invited people in the room to come talk to us. Many did. Dr. Singer came a couple times, Willie Soon, John Christie from the University of Alabama, Roy Spencer's boss, I think. Jack Schmidt, Apollo 17 astronaut, and also a very good scientist, our first scientist astronaut. Although I don't know why they didn't call Walt a scientist astronaut. He almost had a PhD in physics when he went off to fly airplanes.
I wouldn't have liked that.
So anyway, this is what our group of, I've got 32 people on our distribution list, and you know, we have 15 very active, and like we always did at NASA, everybody can critique, everybody can stand up and disagree with you. And that's how you refine a product into something that you're very confident about and can defend. I'm as confident of our conclusions as I ever was trying to advise a NASA manager on a design decision for a spacecraft or an operational decision that was going to be have life or death consequences. So one of my colleagues said, you know, the thing about us NASA guys, when we were right, we knew it. You know, and I look at these climate scientists, they embrace a factor of 3 uncertainty on how much the Earth is going to warm if you double CO2. We don't like that kind of uncertainty. You know, we're going to put people's lives on the line. And we have to know a lot about radiation heat transfer, because that's the way we protect those guys up in space. It's the only way we can get rid of the heat. Okay, so we're an all-volunteer group. That's been covered. We set as our initial goal, I'm doing the wrong thing. Initial goal in the middle, determine the extent to which burning fossil fuels can cause harmful global warming. And the bottom line, I probably won't get through all these charts, so I'll tell you what we concluded. We are going to run out of fossil fuels before the atmospheric CO2 can rise to levels that could cause a climate problem. So we looked at the sensitivity of climate to CO2, but we also looked at how much CO2 are we going to be able to put up over time, because both of those are the two things that you need to focus research on to get the uncertainty out of the forecast. I'm going to skip that because it's just a more detailed discussion of our conclusions. But basically, as Walt mentioned, the climate models are not validated. We ignore them. Our first look at them said they're just not good enough to waste any time on. This chart has been around this conference a lot, probably last year too. It's from Dr. John Christie at the University of Alabama, Huntsville, who presented this chart to the House of Representatives in December 2013. The colored bullets at the bottom are satellite and balloon data, measurements of temperature in the over the tropics and the mid-troposphere, where you're supposed to get this hot spot from human-caused global warming. And the models, these are the latest IPCC models. The average is that solid red line. And over 35 years, they're just starting to vary tremendously from the actual data. And they run these models for more than 1,000 years to figure out how warm we're going to be. if you're going to make public policy decision with something that's bad, you ought to be kicked out of office. I mean, you just don't make decisions with that kind of data. And that's why we focus on the data. So we didn't even like the metrics that climate scientists talk about, because the metrics are all related to something you compute with a climate model, and we weren't going to waste our time with climate models. So we defined a new metric called transient climate sensitivity, and it's similar to what the IPCC calls transient climate response. But the official definition of transient climate response is how much warming will you get if you increase CO2 in the atmosphere 1% per year. Well, the actual rate of increase is about 0.5% a year today. So we said transient climate sensitivity is the rise in global average surface temperature due to the actual gradual rise of CO2 in our atmosphere until CO2 doubles. And starting at 1850, when we had start of a thermometer record for global average temperatures, we're going to take about 230 years to double that CO2 level. I think it's going to happen around 2080. I'll show a chart on that. But CO2 is not the only greenhouse gas. The other greenhouse gases contribute, and aerosols too, which have a cooling effect. The net effect of those other greenhouse gases is about half of what CO2 contributes to warming. So we define this constant beta, which is a number we don't know very well, but it's roughly 0.5, so that the total warming you're going to get when you double CO2 is the contribution from doubling CO2 plus the rise in the other greenhouse gases, and that total warming is what we call transient climate sensitivity times 1 plus beta. And beta is a very uncertain number, but TCS times 1 plus beta is not, and we can use that for forecasting. The point is, TCS is a verifiable quantity. You know, when we double CO2, we'll know how much it's warm, so we'll verify that number. There's no way to verify the numbers and the metrics that the IPCC throw out. Got to sync up here. Walt showed this slide. Walt, you stole this slide from me. I remember you asking me for it. Walt claims he gave that slide to me. But anyway, the thing he didn't talk about is this part down here. We talk about doubling CO2 levels. We started out in 1850 at about 285 parts per million, and when we double it, we're going to be up about 596 parts per million. But we are dangerously close to this green line, which is the absolute minimum CO2 you can have for plants to grow. So when I look at, you know, well, there's no problem on the space station with 5,000 parts per million, and we're talking about doubling down here, we're dangerously close to killing all the plants on our planet. That would be really a climate disaster. So I'm glad to get a little breathing room down here by burning fossil fuels. And you got to put these things in perspective. So this is what people are worried about. This is what we allow astronauts to breathe on the space station. This is the 8,000 parts per million on a submarine. And OSHA allows even more than that for limited exposure. Guys on the space station are staying up to a year now with this level, and there's no problem. This is our projection of CO2. This is what CO2 has been, as measured by different sources. These are from ice cores in Antarctica. The blue part is actual measurements made at Mauna Loa in Hawaii. And this red dash curve is our projection of what CO2 is going to do. It's going to increase, And then we're going to have to start transitioning from fossil fuels to something else because we think we're going to be running out of fossil fuels. And by 2100, our projection is 585 parts per million, and we're looking at this thing peaking at about 600 parts per million. So all of our projections are based on this curve, which if you know the AR5 stuff, this is an RCP 6.0 scenario where the other greenhouse gases are contributing about half of what CO2 does. This is the way climate scientists look at their models. You know, the Earth isn't very important. They really focus on what happens in the atmosphere. I'm going to simplify that for engineers. This is the way we look at it. Here is a 1,000-mile arc of the surface. Here's the part of the atmosphere that affects the surface temperature. It's about 14 miles. You go up to the top of the stratosphere, and then, you know, CO2 is not blocking IR radiation from the Earth. So we got the power coming in from the sun. That's reflected by the albedo. And we've got heat rejection by radiation, and we got some heat going into the deep ocean. So this is the power balance of the Earth's surface. We looked at other sources of radiation from stars. We looked at the molten core of the Earth bringing heat up to the surface. We looked at burning fossil fuels on the surface or rotting wood, and all of those are negligible compared to these numbers that I'm showing. So this is the conservation of energy. The heat going out by radiation has to be 1 minus albedo times the sun coming in minus the heat that's going down the ocean. Simple. I'm trying to make it simple. Okay. But what we have to figure out is if there are changes in any of these variables, how does temperature change? We're saying this is emissivity. This is the way engineers look at radiation heat transfer. A coating on a surface changes that surface from being a black body to something that rejects heat at a lower rate. We're saying emissivity is a function of water vapor, carbon dioxide, other greenhouse gases. And then I'm going to use a little calculus. I don't want to scare anybody, but if I use differential calculus, it'll give me the rigorous relationship between all of those variables. And so I applied some calculus and we get this equation. This just means the change in emissivity due to water vapor, due to the change in water vapor due to heating by carbon. This is direct change in emissivity due to carbon, similar one for other greenhouse gases. And this is a term that comes out of the calculus. This is taking the differential of that term. And this is that other right-hand side. We know what this constant is, the Stefan-Boltzmann constant. We know what the temperature of the Earth average, 288 Kelvin. We can calculate the emissivity from knowing how much heat we're rejecting. We measure that. It's 0.611. And we can calculate this constant, 4e sigma t. It's 1 over 0.302. So that the changes in surface temperature of 0.302 times the changes in emissivity that's a function of these variables plus this other stuff off on the right. And evaluate each of these terms. This is what mainstream climate science says that CO2 does in terms of radiative forcing. This, we're saying, all the other greenhouse gases is just some fraction beta of that term. Water vapor is some feedback times all the heating from greenhouse gases. And we can even throw other radiative feedbacks in there, and we come up with this equation at the bottom that's got water vapor feedback plus other feedbacks times this term. And this is what we define transient climate sensitivity to be. It's the heating you're going to get by doubling CO2. The 3.71 comes from doubling CO2. These are all the feedbacks, and this is the 0.302 that converts radiative forcing to temperature. And we substitute that, we get this equation. that says the change in temperature is our constant transient climate sensitivity times this one beta times the concentration of CO2 every year, plus some other terms. And we came up, this is what the surface temperature data looks like. It's not steadily increasing, it's got some wiggles in it. And if we look back 2,000 years, others have shown this, we've got some wiggles in the surface temperature data that have nothing to do with CO2. So we came up with an equation that models that data. This is the temperature in any year change is the Hadcrut-4 temperature. This is measured, minus the value in 1850. Here's our greenhouse gas contribution. This is a solar radiation contribution. And here's some sinusoids. And we fit the data with that, and it came out a pretty good fit. And this assumes that TCS is just 1 degree centigrade, meaning if you double CO2, you're going to get 1 degree of warming. Here, if we throw in the 1,000-year temperature cycle, we can get even a lower value for TCS. And this is our most conservative value of extraction, and we get 1.2 degrees from it. And if we project out to the 600 parts per million, we're going to get a 1.2 degree temperature increase above current levels. So one other slide. This is our distribution of our uncertainty and equilibrium climate sensitivity. This is what the EPA is using for its uncertainty range. And that's where all these social costs of carbon are coming from. Okay, I've done. Everybody else has talked about our conclusions, so we'll take some questions.
All right.
Thank you.
Thank you, Hal. Now,